Hi folks, and welcome back to the next lecture in the Mastering Python course. For those of you who are new here, and this channel is all about teaching you how to program. Today we'll look at error handling, how to deal with exceptions when things don't go to plan and to prevent your program from crashing. You learn how to create your own exceptions, how to deal with multiple exceptions. We'll even look at debugging techniques and unit testing. Error handling is like having a plan B for when things go wrong in your code. Now, error handling is the process of anticipating, detecting, and ultimately resolving errors that can occur while your program is running. It's really important because it helps your program continue running even when problems occur. Let's start with the basics. Exception handling is a way to catch errors or exceptions that happen while your program is running. The main tool for handling exceptions in Python is the try except block. And here's how it works. We use the keyword try to indicate that we would like to handle any errors or exceptions that may arise in a systematic way, and we follow that by a colon. Then we have our indented block of code that might cause the error, followed by the keyword except, which is indented the same way as the try keyword. Now the error that might occur, and then a colon. Finally, we have a block of code that we would like to execute if that error happens. In this example, we tried dividing 10 by 0, which would normally cause an error and would cause the program to break. But because we put it in a try block and we accepted the specific 0 division error in the except block, our program doesn't crash. Instead, it prints a friendly message telling the user that, oops, you can't divide by 0. Sometimes different types of errors occur in your code, and you can handle these with multiple except blocks. Let's extend our example by asking the user to enter a number. Now we can get two different types of errors in this code, and we handle both of them. If the user doesn't enter a valid number, or if they enter 0, we handle these exceptions differently. We can also add a finally block after our last except block. The finally block is a place to put code that you want to run no matter what, whether an error occurred or not. This is particularly useful for things like closing files or closing network connections, or in some cases closing the connections to databases. Sometimes you might want to cause an exception yourself that is not already built into Python, and you can do this with the raise keyword. In this example, we're creating our own error when somebody tries to set a negative age, which clearly cannot be true. Instead of simply printing out a statement that the age is invalid, we want to trigger a set of events, which we do by raising an error. You can even create your own types of exceptions. Now, this takes a little object-oriented programming, which is something that we'll look at next. But for now, just look at the syntax of defining your own exception class that you can raise and catch in an except statement. This can be really useful when you want to handle specific situations in your own code. And it's good form not to overuse exception handling. It's not a substitute for proper input validation or logic in your code, and it can even slow down your code. Next, we're going to look at some best practices and important techniques to make your code more robust and easier to debug. Let's start with a really important principle in computer science: fail fast and fail loudly. Now, this means that when something goes wrong in your program, it's better to have it crash immediately and give you a clear error message rather than continuing to run with incorrect data. Remember our trusted division by 0 function? Here we're checking for a division by 0 before performing the division. If someone tries to divide by 0, we immediately raise an error with a clear message. When handling errors, it's best to catch specific types of exceptions rather than using a catch-all approach by using a generic exception type. This allows you to handle different errors in different ways, and it's okay to have catch-all exceptions at the end of your except blocks to mop up any unexpected errors though. By handling different types of errors separately, we make our code more precise and easier to debug. You should also avoid empty catch blocks. An empty catch block, which is one that doesn't do anything when it catches an error, can hide problems in your code. You should therefore always include some kind of handling or logging in your catch blocks. Here's a bad example. We are aware that there's something causing a problem in our code, but we're not doing anything about it. Sometimes a simple print statement or logging the error is enough. Here is the same example, but in a good way. We're printing the error rather than just passing. When an error occurs, it's crucial to log not just the error message, but also relevant information about the state of your program. Now, having extra information about the state of your program when the error occurred will make debugging so much easier. Let's look at an example. Here we're using the logging module to log our errors with meaningful information. We're logging both the error and the input data that caused the error. This gives us valuable context for debugging. Sometimes when an error occurs, your program can still continue running with reduced functionality instead of crashing completely. This is called graceful degradation. We can still return data from a function in an accept block to allow for the program to continue. In this example, if we can't fetch detailed user data due to a connection error of some sort, we still return some basic information instead of crashing the program. Instead of stopping the program, we return an expected object, just with data reflecting that we couldn't fetch data properly. Right, we've already had a brief look at the logging module. Let's explore this a little more by looking at how we can track what's happening in our programs. Now, this is a really crucial skill for any programmer. Here's a simple example of how to log effectively. In this example, we're logging information about what our function is doing. If we run this code, we'll see log messages that help us understand what happened even if an error occurred. Python's logging module provides different levels of logging, which we can easily set with the logging.basicconfig method. Now, this method sets the minimum level of severity at which we log messages. You can think of these as different levels of urgency or importance. There are 5 different levels. We have debug, info, warning, error, and critical. And critical is the very, very serious errors that might prevent the program from running altogether. Here's how you might use these different levels in a simple program. We start with debugging information, where we log the data that we're processing. After that, we log a warning in case we don't have any data. And finally, we log info to the logger and errors of increasing severity in the accept blocks. It might seem a little abstract at the moment, but trust me, once you get used to incorporating logging into your code, your debugging is going to speed up a lot and hopefully make it less painful. As your programs grow larger and more complex, you might want to consider using a centralized logging system. This is like having a central archive where all of your log messages are stored, making it easier to search and analyze them. While setting up a full centralized logging system is a little bit beyond the scope of this section, you can start by logging to a file. We can specify the file that we want all of our logs to be saved to when we configure our logger with basic config. This example will save all of our log messages to a file named myprogram.log, and the level we've chosen is the info level. Logging and monitoring are powerful tools that can save you lots of time and headaches when you're debugging your code. As you become more comfortable with Python, you'll find yourself relying on these techniques more and more. Just bear in mind not to log any sensitive information. There are lots of different debugging techniques that will help you make sure that your code performs as intended. Let's look at a couple of these. Now, when an error occurs, Python provides a stack trace, which is a report of all the active function calls at the point when the error happened. You will probably have seen this and it might look quite intimidating, but it's actually packed with lots of useful debugging information. Let's create a function that crashes the program by dividing by 0. This example will produce an error message or stack trace that looks something like this. The best way to read the stack trace is from bottom to top. We can see that the actual error was a 0 division error. Now we have a good idea of what might have gone wrong. Python will also give us the line number in our program where the error occurred, which is super useful. We can then trace back through the function calls to see where the error originated. And in this case, it was in line 2 of the divide numbers function, which was called in line 5 the calculate function. This helps you pinpoint exactly where the problem occurred in your code. To fix a bug, you need to be able to make it happen consistently. And when debugging, try to keep track of the exact steps that led to the error and try to create a minimal example that still produces the error. Often a simple print statement to log variable values at different points in your code is a good first step. We create a function, process data, that squares the data and then returns it. Let's run it. It works absolutely fine for the number 5, because 5 squared is 25. However, when calling the function with hello, we get a type error. By adding print statements, we can see exactly what's happening at each step, making it easier to identify where things went wrong. When we write code to handle errors, we need to make sure that it works correctly. This is where testing comes in handy. Unit tests are small, focused tests that check if a specific part of your code works as expected. When it comes to error handling, we want to test if our code correctly catches and handles exceptions. Let's look at a simple example. First, we create a function called divide that, you probably guessed it, divides two numbers. It checks if b is equal to 0, and if it is, it raises a value error. Now here we're testing if our divide function correctly raises a value error when we try to divide by 0. For this, we use the assert statement to verify that the correct behavior occurs when dividing by 0. We first check that the value error exception raised contains the exact message cannot divide by 0. If it does, the test continues. If it's false, an assertion error is raised, meaning that the test failed. The second assert asserts false, which will raise an assertion error. This is only reached if no exception was raised when we try to divide 10 by 0, indicating that the code didn't behave as expected. In other words, it failed to raise the value error. In our case, no assertions are violated, the test passed, and test passed is printed. Another technique for testing error handling is called fault injection. It's a way to deliberately introduce errors into your system to see how it responds. This helps you find weaknesses in your error handling code. Here's an example. In the process data function, we're artificially introducing a network error 20% of the time to see how our code handles it. Next, we test the system 100 times, each time asserting that we get an uppercase hello back in catching connection errors. When we run the test, we can see that we didn't get any assertion errors, and it displays the numbers of successes and failures. Pretty cool, right? And there you have it, error handling and debugging, piece of cake in Python. Next time, we're going to look at object-oriented programming. This is where stuff gets really exciting, where you can create different objects and make them talk to each other, interact with each other. So if you liked today's content, remember to like and subscribe, and I will see you in the next video when we look at object-oriented programming. Until then, happy coding.